Thanks, Jamil. Can everyone hear me okay? Awesome. So as we discussed, I'm really the doomsday person as we think about viruses in feed mill on really what do we do if the worst happens and we have virus contamination in the mill. And so as we go and start this, I really want to take us back to the 2013 area as PEDV was first introduced into the US and the work we did looking at PEDV distribution in a mill once it's contaminated. And as we can see here, we have an interesting graph. For those of you not familiar working with PCR values in CT, we're going to represent everything today as a cycle threshold value, which is inverse. So the lower the value, the more detectable RNA is within that sample, meaning there's more virus there. And so as we look at our feed mill, we inoculated our feed in this positive batch. So as we can expect with this inoculated batch, we have a greater amount of PDV RNA. But as we do subsequent batches of negative feed, we see that the quantity of PDV RNA is going to steadily decrease, in which when we get to the third and fourth batch after that initial contamination, we find no detectable RNA in the feed, meaning we're able to dilute out that virus in the feed, meaning it should be relatively safe to feed to our pigs. However, as we look at African swine fever, we do not see that same response. Instead, as we look at that fourth negative batch of feed, we still see a detectable ASF presence, meaning we have not successfully diluted out that virus from the feed. And this just looks at the feed itself. As we think about the environment of the feed mill on the whole, we're not actively cleaning the environmental surfaces we see within feed mills. So as we saw in research, not shown today, but as we see in research with this ASF data, that ASF is going to stay on those surfaces and they're going to stay for a long time. Our research demonstrates it's still detectable on these surfaces 180 days after that initial contamination. And so really what we want to look at today is how do we get it out of the mill after that initial contamination. And we went about this through 3 different stages at the Cargill Feed Safety Research Center here at K-State, and we followed everything up with a bioassay using our colleagues at Iowa State University. So we first wanted to look at the use of chemical flushes in these feed mills. So flushes would not be used for animal consumption, but we're going to use something to kind of try to get all of the virus out of there after that immediate contamination using different treatments. Our second objective was to look at pelleting as a method to reduce that viral concentration as a thermal processing method. And then finally, we wanted to evaluate how to physically decontaminate a feed mill, focusing more on the equipment itself. And so starting us off with experiment 1, looking at those chemical flushes, I'm going to take a second to really set up this graph when we start looking at Seneca, which is our first of 3 viruses. When we did this, we inoculated with Seneca, PRRS, and PEDV, so we were able to glean a lot of information from these studies. And so as we think of these flushes, we have 5 different treatments. So we would first inoculate the feed with our 3 viruses and run that through our feed manufacturing equipment, and then we would follow it up with our respective flush. Our first flush was just a control using ground corn. Our second flush was using Salcurb. This would have been diluted in ground corn as well, and would have been included at 5 times the approved dosage, since this is not intended for swine consumption. Our third treatment was using Salcurb at that same inclusion level, and then we're going to add bone builder. So it's a limestone product to be a physical abrasive to try to scrape the equipment itself. Our fourth treatment is a double flush. So we're going to use that bone builder and then follow it up with Salcurb, again at that 5x inclusion level. And then we're going to have our F2 dry. So this is a dry formaldehyde product, which was used undiluted, meaning we just dumped 50 pounds of this dry formaldehyde product in our mixer and saw what happened. And so as we look at these, we're going to see that our bars will represent the percent PCR positive, and then we're going to have either circles or diamonds, and that's going to be that CT value. Again, the lower the CT value, the more virus is within that sample. And as we first just look at our ground corn and Salcurb, we can see an interesting trend, where as we just introduced ground corn in that flush, we do not see an initial reduction in the percent of SVA positive samples. Instead, it's staying up near that 100%. However, in our subsequent batches, so again, these would have been negative batches where we're still just understanding the presence of virus remaining, we do see a decrease, but again, not to the extent we see a decrease as that sow curve. When we implement this chemical flush, we are seeing an immediate decrease in the presence of SVA that's going to continue in these post-flush batches. As we bring in our other two sow curve treatments, we see a very similar trend of an immediate decrease in the percent SVA positive samples. And again, still some samples that are going to be Seneca positive in these post-flush batches. So again, still that risk of recontamination, but much lower than what we saw in that initial ground corn treatment. And our F2 dry, this was our first time we were able to work with this dry formaldehyde product, and we saw really great results in the fact of the decreasing the initial presence of Seneca in this case. As we look at the environmental side, we can see a very similar story in our dust samples, which were collected from non-feed contact surfaces. So these would not be carried away. As we look at the feed manufacturing process, we see a very similar trend, where we see that initial reduction in the SVA presence as we introduce these chemical flushes, and then continue to see that reduction in our subsequent post-flush batches. As we think about these chemicals are going to rest, and as they have these continued contact time with these surfaces, we know that they're going to continue to inactivate and mitigate these viruses as they go forward. As we look at PEDV and PERS, we don't see a treatment effect like we did initially. Instead, we just see, as we introduce the virus in these inoculated batches in all of our surfaces, so feed, environmental, and dust, we, as expected, see more RNA within those samples. But as we look at our flush sequences, our flush, and then our subsequent negative batches, we are not able to see as much detectable RNA as we were with Seneca. And so we were able to follow this all up with a bioassay. So we looked at this to see the infectivity of these samples. And so I just want to start you off with our controls that we utilized to make sure our bioassay itself was working. And so we would first inoculate with negative samples. So these would have been feed from our negative batch of feed, so initially before we introduced any virus into the system. And so as we can see, we saw no virus detectable RNA within those samples, and we followed this up and we saw no infectivity in these animals. Our first positive control was pure virus, so just giving them the respective virus, and as we can see, Seneca and PERS read the protocol beautifully, and we see infection immediately with this pure virus. Interesting, PEDV, although this virus was later found to still be infectious during a virus isolation assay, was not able to cause infectivity in these pigs. So we're kind of scratching our heads as we look at PEDV here. But then as we look at feed from our inoculated batch, we see that this inoculated batch of feed was able to cause infection in both our Seneca and our PERS, for Seneca and PERS. And so bringing in just Seneca pigs, or our Seneca results here first, we're going to have ground corn from the first sequence following the flush, and then the final sequence of the day, sow curb from that first sequence after the flush, and then that F2 dry formaldehyde product, again from the first and third sequences. We never wanted to inoculate with the flush treatment itself, as those would never have been used for swine consumption to begin with. And we can see, regardless of treatment, no Seneca infectivity was observed in these 5 different treatments. PEDV, also no infectivity was observed, but we do have to take this with a grain of salt, as again, that pure virus was not able to cause infection. So maybe there's something there with the virus itself that may not be as infectious as we had hoped. And then finally, we're going to have PERS. And as we look at PERS, we're first going to look at just the inoculum. And so we can see for all 5 of our treatments, we did not find any detectable PERS in the initial inoculum. However, interestingly, PERS decided to go rogue, and we saw PERS infection in pretty much all of our treatments. And so we really don't understand why we're not finding detectable PERS in the initial inoculum, but we saw really, and you're going to see throughout the rest of the day, we saw PERS infectivity pretty consistently. So whether it was a cross-contamination issue or these samples really are PERS positive, just not detectable, is something we'll continue to look at as we continue to evaluate this data. As we look at dust samples from this, we're going to see the same thing. Seneca and PEDV, we did not see any infectivity, but those PRRS pigs are still surprising us, as we again are seeing no detectable RNA in the initial inoculum, but infectivity of these PRRS pigs. And so moving on to our second experiment, this is when we pelleted the feed. So we pelleted at 180 Fahrenheit for a conditioning time of 30 seconds. And so we have these broken down into green, which is our pre-thermal locations, and then red, which is our post-thermal after pelleting locations, so after we applied this heat. And again, starting with Seneca in the feed, we see, as expected, greater concentrations of Seneca RNA in these pre-thermal locations as compared to these post-thermal locations. But interestingly, we still do see some detectable RNA in these post-thermal locations, again, which is a possibility for recontamination if we were just to evaluate those PCR results. As we look at PDB and PRRS, we are seeing a very similar trend, and in both cases, we see almost no detectable RNA as we look at those post-thermal locations. In our bioassay itself, we have our negative pure virus and our pre-thermal feed. We all saw those on previous slides as those controls stayed the same. But as we look at our post-thermal feed, so these pigs were fed feed that was pelleted, we see that once again, no Seneca or PDB infectivity, but our PRRS, that one pig is there just laughing at us and saying that there's something going on with the PRRS itself. And as we get into our final one, we're looking at our physical decontamination of the mill. So with this, our slides, our bars and our CT values are going to be represented the same. We've just changed our treatments. So with this, we have our first treatment is our complete FSRC decon. So this is our normal protocol we would go through after we use viruses within the FSRC. It would include power washing with heated water, followed up by a power wash with Virkon, bleach, and then we're going to heat the entire facility up to 140 degrees Fahrenheit. And once it has reached that temperature, we hold it at 140 F for 48 hours. Our second treatment is going to be chlorine dioxide fumigation. So we're using a pro-oxime product, and we're fumigating that chlorine dioxide throughout these environments we have. And then we take samples 1 hour to allow that chlorine dioxide to have some contact time. Our third treatment is again that chlorine dioxide, but we first removed all organic matter. So we just vacuumed everything up from all of our equipment to try to increase the surface area and decrease the debris that chlorine dioxide would have to kind of fight through. And then for our final true treatments, we used portable heaters. So for these, we had 2 portable heaters that we ran for 48 hours exactly, and we did not need to reach a minimum temperature with these. But we did see temperatures ranging from like 120 to 135 degrees Fahrenheit. And again, we have the heat alone or with organic matter removal. And so as we would hope, considering this is our standard protocol, our complete FSRC decon, after we did all of those steps, eliminated all Seneca RNA from these samples. As we look at chlorine dioxide, we don't see the same effect. We see very little difference between the initial inoculation of these pieces of equipment compared to the post-treatment samples, regardless of whether we removed organic matter or not. And finally, with heat, we see a very similar story. We do see a bit of a difference here in this heat as we remove organic matter, but overall, we still see a pretty consistent presence of Seneca in these samples. While not shown, PDB and PRRS had a very similar trend, but as we saw with the feed and experiment 1 itself, all of these numbers are just lowered. So we just see less of the initial inoculation of PDB and PRRS, but still a similar trend of finding the results here. And as we go to the bioassay itself, again, we have our negative and pure virus control stayed the same. But as we look at the positive environmental control, we only saw Seneca infectivity from these inoculated samples from these surfaces. But as we look at Seneca infectivity after treatments, we see no Seneca infectivity nor PDB infectivity. But once again, we are seeing PRRS infectivity. As we look at this, the only treatments lacking PRRS infectivity is that complete FSRC decontamination and that heat removal. But again, considering our heat plus organic matter removal still had a PRRS positive pig, it might have just been a one-off as we think about the trends we saw with PRRS. We also looked at just the removal of organic matter alone. So after we vacuumed up those samples, what happened? And we see a similar trend where PRRS positive pigs were the only pigs showing any signs of infectivity. So I threw a lot of information at you, so really what do we get from all of this? And as we look at it, we saw for the most part our different treatments worked. We saw flushing treatments that worked, we saw thermal processing that worked, and our mill decontamination worked when we look at those bioassay results, except for PRRS itself. So that PRRS is really throwing a wrench in things, and we continue to be evaluated to figure out if it was just this experiment or if this is a continued trend we're seeing as PRRS continues to evolve within the industry. But what can we take from this? What can you guys do today as you think of your mills? And we're still going to tell you that biosecurity and prevention are key. As Jamil talked about, we're having new protocols put in place to exclude high-risk ingredients or having those quarantine processes in place. Furthermore, we want to continue to preach that extending your biosecurity at the mill itself, but especially as you're going from farms to mill, is going to be key. But these active mitigation techniques we talked about today can be implemented as we think about them, and especially as we think about just taking PCR results alone, which is what a lot of our mills may think to do. That thermal processing and those chemical flushes seem to do the best on a PCR basis. But again, other than PRRS, our bioassay shows that we have promising results for all three of our strategies looking at going forward.